Hello everyone, I'm Xiao Gang. Okay, let's write this simple conversion test code. Well, let's start writing this code here. Let's call it trustful. Let's call it conwait. We usually like to use conwait. And similarly, we'll do it this way. Obviously, if we want to write a shared pointer here, we better do it like this. Okay, declare it like this. Let's add one more from the front. Another reference, a shared reference, like this. Okay, so now we have a shared reference and we want to convert it to a shared pointer. That's very simple. You can just copy it directly and then perform the conversion, right? This is completely fine. And if we want to convert the shared pointer back to a shared reference, then how should we do it? We must perform a null check because it could be null. If it is null, there will be problems if we proceed. We can check it like this. That is, if it is outside, click here. If it is outside, if it exists, then we use a shared reference to catch it here. We call it bank reference. That is, it comes back again. And here, we can call a function from here called TOSharedRef. You see this line? Okay, we can take a look at the description of one of its functions. It converts a shared pointer into a shared reference. Must be wired. Or an acceleration will trigger. That is, it will trigger the assertion. Check. You can see. Check. We can make it trigger. Let's just skip this part. Then if we here, we are operating on an object anyway here. We reset it. Now it definitely won't work. Then we execute it again. Banker reference. Then we trigger this assertion on our side. Banker reference long. Okay. Good. Now let's execute this breakpoint code. Then we set the breakpoint. We directly enter the byte. Good. Our side is already written. We directly enter the assertion. Okay, we're in. Obviously, our side is okay. Here, a shared reference code is declared, and it is 4563. You see here, 456, right? Then these two 456 have also finished executing. If available, we'll create another shared pointer. This shared pointer is immediately acquired, so no need to worry about it. Then, because you'll notice, the current reference count, barring any surprises, should be 2. Okay, we can take a look. Right, the reference count is 2. Then, we release it, and actually, now we need to look at this reference. Take a look at this reference. Actually, right here. We haven't triggered an assertion yet. We go ahead and trigger the assertion. Right. There is a problem here. This time it's placed. Its reference count should become 1. And then here, we are using an empty 1, which triggers the assertion. We've already found that our program can no longer it seems to have passed. If it passed, ignore it. Okay, we crash. So this place will trigger this assertion called check is wide. Okay, then let's continue looking below. And then it's about comparison. Actually, how do you determine if pointers are equal? You can actually just determine it like this. Because they are compared, they are only equal when the equal sign points to the same referenced object. Let's write out this equal sign first. Let's call it EQ. I've already forgotten this. Forgotten how to spell this word equal. It's a bit long, I think. Okay. This place has 2 pointers above. Obviously, both pointers are currently empty, so they must be equal, right? So there's really nothing to judge here. Since they are equal, we'll just leave it. Then we'll add another one here. We'll give it an A1. Okay, this shared pointer. We'll do it this way. Okay, then we let load B. Or we can just set load B equal to this. Okay, then the two of them, if they check for equality, they will definitely be equal because they both point to the same object. Let's print a log. Okay, log. And here, warning. Okay, they are equal. Okay, let's call it equal. Okay, that's fine. Then let's see what's written later. Then here you can check whether it references a valid object, but sometimes both methods are the same. That is, this is actually an overload. See if it references a valid object. Then here you can get this pointer and check if it's not null. Actually, these several methods are all can be used to check if it's null. We can put it here. Now this loader is obviously null, right? Because it points to this object, it is not a valid value. Let's put one here. Let's put a log here for everyone to see. Let's call it the drop A is empty. You can see that this gate actually, it returns a this struct. You see, I can zoom in a bit. The pointer of the struct. This pointer should not be null if your gate is valid. Okay, no problem. Let's continue looking below. And this part is a dereference. That is, if this side is useful, then you can directly call the object inside it. This part, then you can do it this way, by calling it like using a normal pointer. It's fine. Then you can first get it. You can get this pointer and then call it. That's also fine. Or after you dereference it, then use the dot to access it. That's also fine. Okay, then let's write it together. Then it's quite obvious. Our loader is completely fine. We'll do it this way. We use Noda, and then let's take a look. It's a shared reference, so it will definitely have a value. Then we need to use node B, right? Next, what we need to do is inspect the values inside. We'll also demonstrate it in these three ways for everyone. We might need to add some methods. It's the constructor now. Then we give it a print. Print A. We'll just write this here. We'll also write a log, print AA. Now print this A. Then here we are. We dereference it using these three methods to call the methods inside. The first method is the most common one. We can just do it like this. It is completely fine. The first method directly dereferences it using the smart pointer. Then the second method, actually, when you call get, what it returns, we write it like this. Writing it this way is clearer. It returns a pointer, and then you can also print R here, that's fine. Actually, you can omit it here. That's also fine. Yes, because it returns a pointer for the next step. The third method actually dereferences it. You can see it's a dereference, so you can write it like this. Because of this operator, you cannot do it this way. You must put this in front. Yes, because you need to dereference it first. Right, then we click print AA. Okay, now let's set a breakpoint and test it. Let's set a breakpoint and test it directly. We'll set a breakpoint here. Set up by TWeakPtr. Okay, after entering, we declare two empty pointers. These two empty sub-objects become equal. We said we did nothing. Then we made one over here, lose a 1, then copied lose A1 to make B. Then lose a 1 and B there, and B is still equal without asking any questions. Okay, this place, it's all code optimized. Because you will find, because here, it seems we wrote it wrong. Yes, because this place is all empty. These three are all empty. He just jumped directly here. Then execute this part. You can see everything executed smoothly, right? So obviously we have finished executing. Then here we need to go to a reverse. There's nothing to verify here. Didn't start a reverse, right? We don't need to reverse. We just need to change this comment. Let me check if it's available. Actually, we didn't even use this, so it's completely unusable. You see, let's first look at the last one. The last one is very useful. It can define a deleter. Then it does this by passing such a large method, doing it this way. So, obviously here, take a look. This is a deletion function code. And then here, it declares the responsibility. And then here, it passes such a large value. Then it calls this method. So that's how it is. Actually, you don't need to. This thing, you doesn't need to write it. No need to put it in this position. Writing it in this position actually looks a bit nicer. Let's write a deleter for everyone. Hey, this part is a bit redundant. It might cause some misunderstanding. Just pass a name directly. Let's call it delete. Okay, if we call it delete, let's go and we can see it is declared here. I thought fun was a pointer. Then we can just copy it over here and the struct here. We use the same struct. This is our struct. And the lambda here, it will pass a fixed parameter. Then now we need to write a... What do we need to write now? Write a method. We can write it here. Let's still print a log for everyone. This way it's simpler. Okay. Then for the content of this log, we'll just write it manually. Let's call it custom deleter. Deleter. Good. Let's call it custom deleter. And here it is obviously a shared reference. So here is a custom deleter. Then it is a shared pointer. What we need to do? Actually, this thing, we change the AA inside it. We change it to 558. We change it to 558. Okay. Then here, we change the C to 559. Of course, you can perform many operations. Many operations, yes. Sometimes we want, after a piece of code, to perform some restoration or operations. Usually, you would write it like this. Write a piece of code here in the middle. Then let me show you another way. We call it O2 my lambda. Sometimes you would write it like this. That is, you can define a member function's progress method or something, but you can also write it like this. We need to copy this over, copy it like this. Let me take a look. Okay, then we need to define a custom functor my lambda, and then we give it a 16. Then at this point, we declare a shared pointer. Let's call this flow point 2. Okay, we haven't passed this a character, so when we construct it, it should be the default character. Don't worry about it. Let me check the shared pointer. It needs to be written like this here. I almost wrote it here. Missed it like this here. Hey, you can see that this thing can be reused. There's no need to copy the same code again. This is more concise. Because this function might only be used here, you don't need to write it outside. Because the place you write, it might not use it. Then we'll set a breakpoint here. Just set a breakpoint here. It seems like you can write it this way here. Then let's comment it out. Comment it out. You can't write it this way here. It won't compile. This is related to a certain version. Can't write it this way. We'll just put it here because we'll have a writing style like this later. That is, define a lambda, then pass this lambda over. Then there's no need to reuse this function. Later, we will teach you how to write this in Slate. Okay, then we will just set the breakpoint here for you to listen. Okay, our breakpoint here has been hit. Actually, we should be able to set breakpoints inside it as well. It doesn't seem to hit here. If it doesn't hit, we'll just ignore it. Okay, let's observe our log here. Then we execute. It can be constructed. Then we execute construction again. We go over again. You will see a custom deleter for the shared pointer. Custom deleter for the shared reference. Let's go further back. You can see we're done. Okay, right? We executed it. It's just that when we were purchasing cake loop, right here you can see it clearly walked in. What about our purchase? It's this part doesn't seem to have printed. Let's check again. Maybe if you do it this way here, we are taking these paths. Then this destructor was not executed. You will notice, yes, that is to say, it is a custom deletion of a struct. So you need to pay attention to this point. Let me show you again. pay attention here. We can see here we can set the breakpoint. You will notice it actually didn't enter, because if it entered, it would log this. You will notice that this destructor was actually not executed. Okay, let's continue looking at our logs. You see, it was a custom deletion. So everyone should pay attention to this detail. Okay, we'll stop here for this lesson. The sharing index is still very simple. It's quite clear, I think. Okay, in the next lesson, we will just briefly go over the rest. Thank you, everyone.